All right, welcome. This is video number 2 in our atomic structure unit. You're going to need your notes open to where it says video number 2. You're also going to need your periodic table open. And if you have a calculator app open on your phone, that would be helpful as well in this video. In this video, I'm going to be talking about the anatomy of an atom. What are the components of an atom? Where are they? What goes where? And also the definition of the word isotope. So these are things that should be a review from the POGL, but we're just making sure we're all clear on them. So first up, subatomic particles. Well, the word subatomic, before we fill out the chart, is composed of 2 bits. We've got the sub bit, right? And that means, if you think of the word submarine, what does sub mean? It's something that goes under the water. So sub means under or beneath. And then obviously we have the atomic bit, which would just mean atoms. So if you combine it, the word subatomic means under the atom. So the subatomic particles are the particles that are inside the atom. And those in chemistry are electrons, protons, and neutrons. So symbols, what's the symbol for an electron? We say an E with a negative sign. Proton is a lowercase p with a positive sign, and neutron is a lowercase n with a little 0 written in the top right-hand corner. And this has to do with the electrical charge, because the upper right-hand corner is always where we write the charge on something in chemistry. So the charge on an electron is -1. So don't just tell me negative, but tell me -1. A proton is +1. And a neutron is neutral. The mass in AMU, or atomic mass units, an electron has a very, very small mass. Its mass for us is approximately 0. It's not truly 0. There is a mass to an electron, but it's so small in comparison that we say its mass is approximately 0. A proton, on the other hand, has a mass of 1 AMU, so that's very massive in comparison with an electron. And a neutron also has a mass of 1 AMU. So notice that the proton and the neutron, they have the same mass, because that's going to be important. Location in an atom. Where are electrons in an atom? Electrons are in orbitals, which are in shells, which are on the outside of the atom. They're not in the center. Versus protons, where are those? Those are smack dab in the nucleus, as are neutrons. Neutrons are also in the nucleus. And this diagram is simply illustrating that. So we have a picture of a carbon atom, and we have our nucleus in the middle. The nucleus, in comparison with the rest of the atom, it is small, it is massive, meaning it has a lot of mass, it is dense, and it is positively charged, because what we have in any given nucleus are protons and neutrons. Protons are positive, neutrons are neutral, they don't have a charge, so overall our nucleus is positively charged, right? Nucleus, protons and neutrons. And then outside the nucleus we have electron shells, so this would be 1 electron shell, and then we'd have another electron shell. Now notice this one is closest to the nucleus, so I'd say that that's shell 1. The next one up, it's farther away, so that's shell 2. And remember, the further away you get from the nucleus, the more energy the shell has. So this shell would be lower in energy, and this further shell that's out would be higher in energy. And then we also, obviously, in the atom, we also have lots and lots of empty space. The atom is mostly empty space. Anatomy of an atom. Again, subatomic particles, protons, neutrons, electrons. I mention it again in case a problem ever asks you to explain in terms of subatomic particles. You want to mention those 3 possibilities, protons, neutrons, or electrons. But we can also include this other word called nucleon. And a nucleon is a subatomic particle that is found in the nucleus. So subatomic particles found in the nucleus. And we can tell this from the word, because if you look at the word nucleon, it kind of has this bit where it's starting like nucleus. So what are the subatomic particles that are found in the nucleus? Not electrons, but protons and neutrons. So together, I'd say that protons and neutrons, that these guys, we can also call them, when we're talking about them together, nucleons, because they're subatomic particles that we find in the nucleus of an atom. Super big vocab word, atomic number, which hopefully you remember from the POGL and you feel pretty confident about from that. It is the number of protons, and it is unique to each element. You change your number of protons, you change your atomic number, you change what element you're talking about. This is a huge idea in chemistry. The periodic table is actually organized by increasing atomic number. Every time you change the atomic number, you are changing the element. The number of protons, because that's what it is, identifies what the element is. You change your protons, you change your element. Now, where do we write the atomic number when we're notating around an elemental symbol? We always write it in the bottom left-hand corner. So the bottom left-hand corner around any kind of symbol, if there's a number there, that's going to be your atomic number, which is your number of protons. And we can also find it right on the periodic table. If an atomic number has not been given to you, but you know the symbol, you can look up the symbol and find the atomic number on the periodic table. Mass number is quite obviously the mass of an atom. Now, this is not the same as atomic mass. Atomic mass, and I know it kind of sounds very similar, but atomic mass, which is on the periodic table, is actually an average mass for lots of atoms. But a mass number is just the mass of one individual atom. So we're going to be focusing on mass number right now. What is the mass of an individual atom? Well, what are the subatomic particles that have mass? Protons have mass, about 1 AMU. Neutrons have mass, about 1 AMU. So if you sum them together, protons plus neutrons, you get your mass number, the mass of an atom. When we write the mass number, it's always going to be in the top left-hand corner around a symbol. Or if we're writing the word for the element, it would be the number that follows the element name. So we have, for example, this right here, top left-hand corner, C14, or I could write it as carbon 14, that number that follows. All of this is saying that the mass number for this particular carbon is 14. Well, what does that mean? Well, we know that it's carbon, so we can go to the periodic table, find carbon, see that carbon has an atomic number of 6. So we know that carbon has 6 protons. Its atomic number would be 6, but we know its mass number is 14. We also know that the 14 must be equal to the protons plus the neutrons of this atom. So if we sub in, we know that there are 6 protons. In carbon 14, there must be 8 neutrons, because 8 neutrons plus 6 protons is going to give you the mass number of 14. And then finally, nuclear charge. Well, this is a very descriptive word, and I love descriptive words in chemistry. I love terms that essentially tell you what's going on. Nuclear charge. Charge of what? Charge of the nucleus, because the word nuclear quite literally is an adjective used to describe anything to do with the nucleus of an atom. So nuclear charge, charge of the nucleus. It makes sense. It's a great descriptive word, charge of the nucleus. But here's the thing, the nucleus, it contains protons and neutrons, right? Well, protons are positive, neutrons do not have a charge. So the charge of the nucleus, first of all, it's always positive. You're never going to have a neutral or a negative nucleus. But what charge? What is the actual charge of the nucleus? We're just focusing on the thing that actually carries a charge. The nuclear charge will always be the same as the number of protons that that particular atom has, because those are the things in the nucleus that carry a charge. So if we go back to this carbon example, carbon contains 6 protons, so that means that the nuclear charge for carbon is plus 6, same as the number of protons. An atom is electrically neutral. This is a huge thing. When we define atom, we can define it a number of different ways, but in terms of charge, by definition, an atom is electrically neutral. What does that mean? It has a charge of 0. There's no charge on an atom. Yes, we can take an atom and we can alter it, we can make it into something else that now does have a charge, but it would no longer be considered an atom. The word would change. When we use the word atom, we mean electrically neutral, we mean charge of 0. Well, what are the subatomic particles in an atom? We have protons, neutrons, and electrons. Protons and electrons carry a charge, neutrons don't. So this means that in an atom, the number of protons in the nucleus, the positive charge in the nucleus, must be equaled out by the number of electrons in the shells in order to keep the overall charge neutral, in order to keep the overall charge 0. So the amount of positive in the nucleus is completely balanced by the amount of negative on the outside. Putting it another way, your number of protons must equal your number of electrons for an atom. This will always be true for an atom. So looking at an example of this, we're going to work out subatomic particles for this silver, Ag is silver, and for this lead atom. So just a reminder again that what the numbers that are written around it, the number in the bottom left-hand corner, that's the atomic number, and the number in the top left-hand corner, excuse me, is the mass number. And what does atomic number mean? Atomic number means number of protons. What does mass number mean? Mass number is equal to protons plus neutrons. So if I'm working out the protons, neutrons, and electrons in this species, I automatically know that there are 47 protons because of the atomic number. Now, in order to work out the neutrons, this is saying that there are 108 protons plus neutrons in this thing. So 108 is equal to protons plus neutrons. But I know that of that 108, 47 of them are the protons. So if I subtract away the 47 protons from the 108 protons plus neutrons, I can get the number of neutrons. So 108 minus 47, there are 61 neutrons in this thing. Because that way, 61 neutrons plus 47 protons gives you the 108. And number of electrons, well, this is an atom. Again, and atoms are electrically neutral, which means that the number of protons must be equal to the number of electrons. That these guys have to be the same for an atom. Going over to the lead example, again, bottom left-hand corner number, that's our atomic number. That's our number of protons. Top left-hand corner, that's our mass number. That's our protons plus our neutrons. So not just the protons, but the neutrons is added in as well. So filling out our subatomic particles for this, there are going to be 82 protons, I can tell from the atomic number. For the number of neutrons, I'm going to subtract away the number of protons from the mass number, right? I know that 207 is equal to 82 plus the number of neutrons. So if I simply do some subtraction, that gets me that there are 125 neutrons in this thing. And for electrons, again, for an atom, number of protons must equal number of electrons in order to make it electrically neutral. And then finally, the word isotope. This is a super important vocab word for us that we're going to see again and again and again throughout the year. So this is a really big word. Atoms, again, we saw this in the POGL, so hopefully you feel comfortable with it too. Atoms that have the same atomic number, but different mass numbers. That's what isotopes are. Same atomic number, different mass number. Well, how can you get that? How can you get atoms that differ in that regard? Putting it another way, same number of protons, different number of neutrons. It has to be the same element. That's what the number of protons is saying. But it has to have a different mass. Same number of protons, different number of neutrons. Same atomic number, different mass number. So we've got two examples of this, carbon 12 and carbon 14. Notice here, right, they're both carbon, so same element, right? But the mass numbers are different, so different masses. That's what makes these two things together isotopes of one another. Same element, different mass. Looking at another example in actual terms of numbers, we have some yttrium examples here. I asked my AP Chem kids what element I should use, and they picked yttrium. So, blame them for the weird symbol. I've got yttrium 89 and yttrium 91. Now we can fill in the atomic number from yttrium from the periodic table. So we look up yttrium, we see that it's atomic number 39. So again, same atomic number. Both of these guys have 39 protons. But in order to figure out the neutrons, we would subtract the mass number from the atomic number from the mass number. So this first yttrium, yttrium 89, has 50 neutrons, and the second yttrium, the yttrium 91, has 52 neutrons. But so they're isotopes, so because they have the different number of neutrons, right? But the yttrium 89 has 50 neutrons, and yttrium 91 has 52 neutrons. electrons. Again, same number of protons, different number of neutrons. Big definition of isotope there.